Hey everybody, this is Kerry. I'm not going to talk like that. I'll kill myself. Or you'll kill me. So this is Kerry with packetbomb.com. This is another video in the It's Not the Damn Network, you guys series. I'm going to show you some things you can look for that can impact performance, but they really don't have anything to do with the network. So I strongly recommend you read the write-up I wrote previous to this about throughput and TCP windows, a receive window, congestion window, send buffers. If that doesn't make any sense to you, go read it. It won't take long. So let's just jump right in. I've got two captures. One is going to be sender bound. One is going to be receiver bound, meaning the bottleneck is the receiver on one and the sender on the other. So let's jump right in. If you recall the last video, we had a default layout to Wireshark, but we added a delta column. We added in the sequence number columns. So we've got this capture, and what I want to know when I'm looking at throughput is, what's the round trip time? If I'm working with someone, I can just ask them, but if they don't know, or they can't tell me or whatever, you can look at the three-way handshake. So this, I know, was captured on the client side because the delay is between the SYN and the SYNAC. The client sent the SYN, it had to go across the network, the server had to respond, and it had to come back across the network. So the round trip time is about 98 milliseconds. If this were taken on the server side, then the delay would be between the SYNAC and the ACK. Just think about it. Okay, so we know that's what we're kind of dealing with, is around 98 milliseconds. So you know that when I'm troubleshooting performance, I like to look at the TCP stream graph. So you need to, because the stream is one direction, you got to click on a packet that has data in it and the data flow. So I'm clicking on one of those packets, and I'm going to bring up the TCP trace graph. Okay, so let's jump in down here at the beginning. You can see what would appear to be slow start. And then there's an abrupt change where we're doing, what appears to be slow start, and then it just stops, and then it just shoots out a bunch of data. So I want to see what's going on here. So I'm going to zoom in. Let's start at the beginning of this. I'm going to click on this packet, and I'm not going to go over what this graph is. I've written about it on my site and I talk about it in previous videos, but this is bandwidth. This is bytes over time. So click on this segment. Yeah. Okay. And we'll bring this down out of the way. Now, so what I want to do is add a column. I want to know about my bytes in flight. So I can add that as a column under TCP, under sequence analysis. And remember, the things in square brackets are just Wireshark informational stuff. It's not actually in the data. It's not in the header or anything. Apply as column. Boom. Okay, so what this tells me is on this packet, the bytes in flight at this point in time is 1460. Now I can see that the amount of data in this packet is 1460. So what that tells me is there's no outstanding data. We're all, from this acknowledgement, we're all acknowledged up. So this is the first data out on the wire because everything else has been acknowledged. So I'm going to kind of follow this along. From that graph, we sent a whole bunch of it at one time. So I'm scrolling down, I'm looking. And one thing that catches my eye is this packet. Why? Because it's a power of 2 boundary. That is exactly 64K. That is something that should jump out at you. Additionally, what else jumps out at you? This push flag. If we come over here to the length of this frame, previously they were all maximum size, 1514. So MTU of 1500, 14 byte Ethernet header. And then we have the smaller one. So with the push flag and a smaller bit of data, what that tells me is we've reached some kind of data boundary. Obviously it's 64K. So to me, that's either the application sent 64K to TCP, or the buffer size, the send buffer size is 64K. Now, there's no delay. We don't stop sending data. So our congestion window is open enough. Our receive window is open enough. And apparently there's enough room in the buffer to buffer this previous data, because we can't remove data from the buffer until it's been acknowledged by the remote side, because we may have to retransmit it. So we continue sending data, scroll down, and then here's the last one. This is exactly 128K. It's a push flag again. Same thing. We got full frames and then the whatever's left over. So another 64K. So we sent two 64K chunks back to back, and then we waited a full round trip time for the acknowledgement. So we would not send more than 128K. So that could be, it could be congestion window, or it could be the buffer size of the sender. Now, if we look at, say, the receive window, that's this packet, it is a megabyte. And we've not had any data loss yet. So we're, right now, the slow start threshold, the congestion window is set to the initial congestion window, which usually is some arbitrary high number. A lot of times it's going to match the receive window. So this limit is probably not the congestion window, it's probably the buffer size. So either the buffer is 64K. Well, I'll just tell you, I know the buffer size is 64K. At least that's what the operating system reports. This is Windows. However, clearly the bytes in flight to this time is 128K. Now, when the application sets a buffer size, this is sort of a suggestion to the operating system. So what this tells me is, even though the buffer is 64K, or it says it is, it actually has enough room of double that, of 128K, because it sent 128K in flight without acknowledgement. So clearly it can buffer more than just 64K, but the congestion window is most likely much higher than 128K. So I'm going to say that this is, bound by the buffer size. So we wait for all these acknowledgements to roll in. We send like a little bit of data here. It's like 2 bytes. It's probably just some iPerf stuff. And then we start up again. We start back. Everything's acknowledged. How do we know? Well, there's a couple ways. One, because the bytes in flight is 1460, and this packet has 1460 bytes of TCP data. You can also look at the acknowledgement number, scroll back up. So it's 169. Scroll back up. 169 was the last thing we sent. So we know we're all acknowledged up, and we do it again. So this repeats itself, this pattern, over and over again. We send 128K, we stop, and then we wait for acknowledgements. This flat spot down here is where nothing's happening. We're just waiting for the data to make it across. The first 2, because TCP is going to acknowledge every 2 packets. And then the acknowledgements start rolling in, 1 for every other packet. And once we acknowledge, they all roll in. Off we go again. Now, we can also see from this graph that the receive window is way up here. So there's all this space in between. All this space is available buffer space. This is time. So if a straight vertical line is 1 moment in time, I'm not going to sing that one. So the space from the top of this line up to there is the amount of free buffer space on the receiver. So plenty of room, right? So to me, the issue here is, considering there's no packet loss, so the congestion window should be open enough to match the receive window. The issue here is the send buffer is not large enough for the BDP of this connection. Okay. Is there anything else I want to say? I've mentioned, what I think the congestion window is. A couple of ways you can kind of estimate it is based on the bytes in flight. But of course, if you're bound by the size of the the send buffer, that's not really going to help you a whole lot. On Windows, there's this little program called TCP Analyzer that comes with the SDK. If you download the SDK, go digging in like a bin directory. It's like a graphical net stat. If you click you click on a connection and hit stats, and it'll bring up another window that shows you like the congestion window, the round trip timeout, the number of fast retransmissions, all kind of really cool TCP stack state information. The only downside is, as far as I can tell, you can only start it on an established connection. So if I want to see the stats from the very beginning of a connection, I don't know how to do that, because by the time you can click and find it, the connection's already been going. If you're on Linux, you can use socket statistics, the SS command. I think it's -E or maybe -I to give you congestion window and slow start threshold and all that. I'll put something in the write-up under this post. Okay, so let's switch over to the next one, which by process of elimination must be receive window bound or receiver bound. So same thing, we start at the, let me just go ahead and add bytes in flight to this one as well. So right click bytes in flight, apply as column. Gonna go to the beginning. These are the same host actually, running iPerf, so it's the same round trip time. So let's click on a data packet. Let's bring up TCP trace graph. Have a look. So if we zoom in towards the beginning, we can see we have the same behavior as before. We got slow start starting up, and then the difference here is, and you can see then it goes back to shooting out this data all at once. The difference here is, this top line, is the receive window. We run into it, or we get really close to it. Actually, we don't. There's just a few bytes left, but we can't send another full packet. And then over here, we start sending out our data. But on the previous one, we did 128K. So this one, if we click and go there. 1460. So this is the first byte out the door after everything's been acknowledged. Scroll down. Let's open this up a bit. So we get to 64,240. So the difference between that and 64K is not quite, again, a full size frame, and it doesn't send. So it waits for a full round trip time for an acknowledgement. Again, an acknowledgement acknowledges 2 packets. So we send, that opens the window up a little bit. We send 2 packets, and then we just kind of limp along like this. Acknowledgement, 2 packets, acknowledgement, 2 packets. So what that looks like is, if we zoom back out, so we send up to the 64,240 to here. We have to wait for the round trip time, and then we limp along sending a couple of packets for every acknowledgement until we finish sending however much we need to send, probably another close to 64K. And then we do another sending out this data. Man, it's hard to hit that just right. Oh, I did it. So there we see we actually hit exactly 64K, and it says TCP window full. So we sent all this data, just one after the other, no delays, until we filled the receive window. If we look at this acknowledgement, the receive window, 64K. So we filled it. We have to wait for an acknowledgement. It's a full round trip time. That gives us 2 more packets, and here we go, limping along at 2 packets for every ACK to finish out probably another 64K. Then the rest of the acknowledgements roll in. The rest of these acknowledgements roll in, and we just repeat this pattern over and over. We send 64K, we fill the window. When the data here reaches the top line, we've filled the receive window. We can't send anymore. We wait for the window to open a little bit, and we limp along a couple of packets at a time. And we repeat this process over and over again until we send all of our data. So why isn't the receive window opening more than 64K? Well, if we go back to our beginning, so the client says, hey, I can use a window scale, but I'm not really going to use it. So whatever I acknowledge and send to my window size value, that's what it really is. But this is the client who's sending the data. Who cares? The server, the SYNAC, is the one receiving the data, but it does the same thing. It says, yeah, I know about window scale. It's cool stuff, but not going to use it. So it's limited to 64K. And if we go to stats, IO graph, let's make this bigger. Change this to advanced. We will do, let's say, a maximum of TCP.window size. And I only want, both sides always include a window size in their TCP header. I only want to graph the window size of the receiver. And his source port is 5001. So if I graph that, let's change this to like this. This is, 64K. And then these spots in between are when we're receiving data and not sending any acknowledgements. If you go back here, you can see this is probably a slow start, like single X and then a couple of X, and as we send more and more data. So let's say I want to graph the average of the bytes in flight. TCP analysis, bytes in flight. And bytes in flight is only in the header when it's someone who's sending data, so I don't have to filter on any particular side. If I graph that, and that's not line, that's F bar, but whatever, that's fine. It's kind of cool here. You can see how we start out with slow start, as we build our congestion window, because it starts off at like, 2. We can put more and more bytes on the wire at a time, and it builds up until it almost hits our receive window, and then it does. So this is a point where we're sending 64K, and then we have to wait, round trip time, and then we can eke out a few packets at a time, and then that repeats itself over and over again. So that's kind of a cool visualization. Okay, so to recap, our first capture was sender bound because the send buffer wasn't large enough to fill the pipe. So we had a lot of unused space in the pipe that we weren't using. So for that one, you want to go to the sender, and you need to either adjust something on the operating system or the application. And then for the other one, the receive window wasn't opening up. Either the application is specifically setting it to this value of 64K, which is true in this case, or the operating system has it configured that way. So if you see something like this, then you can go back to whoever's complaining and be like, look, bitch, this is not the network. Fix your shit. Excuse me, I get worked up sometimes. So what do you think? I did want to say on the one this one, do you notice that sometimes we only send 64K at a time and then we wait a round trip time before sending the rest? It happens a few times. Here's one. Other times we send all 128K. I'll put this capture up. Have a look at it. See if you can figure out why. Yeah? Cool. Email me. Let's talk about packets. I talk to people all the time on email about packets. Love it. Carrie@packetbomb.com. Join the email list. You'll get some additional videos, and those are my favorite people. So yeah, thanks for watching. I hope you think this is cool stuff, because I do. And if you don't, just stop.